Hi guys, welcome to the calculus class minus Ms. Lucas. Um, I am out today, but I'm recording this lesson so that you don't go a day without learning calculus. Yay! Okay, so anyway, we are starting chapter 4 now, and this is a chapter in which you get to use the derivative. That's right, all the rules and everything that you've learned about the derivative, we are now going to put them to work. And the first topic up here is called the first and second derivative tests. First and second derivative tests. If you have a note template, you can pull it out now for the first and second derivative test. I hope you do. It'll make your life a little quicker. Otherwise, you can go to the Moodle page and print mine out after class because these notes will be up for your perusal. All right, so using the derivative, we have to remind ourselves of a few key ideas, a few terms to start off with. The first one is, what is a critical point? A critical point for f are x values in the domain of f such that the derivative f of, we'll call the critical point, or the x value of the critical point c, such that f prime of c is either equal to 0 or f prime of c is undefined. That is the definition of a critical point. And please note also that they are x values that are in the domain. They have to be in the domain. So for example, even though the derivative of 1 over x at 0 is undefined, since the derivative of 1 over x is negative 1 over x squared, we see that it's undefined at 0. 0 would not be a critical point for this function because 0 is not in the domain of the original function. Okay, so you can't call 0 a critical point for 1 over x. These are really important points. They are critical to the derivative, to the function, because they are candidates for local extrema. So that's why we're very, very interested in them. That's our first step in finding and identifying local extrema. The second steps would be the first and second derivative test, which we'll get to the first derivative test today. So, and note that between any two critical points, the function must be monotonic. That means it's either increasing or decreasing, and we know that's for sure. Now, they're candidates for local extrema because, quite often local extrema happen where the derivative is equal to 0. For example, that's a local max, local min, maybe where the derivative is undefined might be a local min or a max, but it's not necessarily the case. For example, if I drew a cubic, you guys know that the derivative is 0 right there, and yet we don't have a local extrema. So it's not correct to say that a local extrema occurs, that a critical point leads to a local extrema, because it doesn't always. It is correct to say that local extrema occur at critical points. We can say it that way, but we cannot say, critical points all lead to local extremas. So, just a reminder of the derivative signs. We know that if f prime is greater than 0, we know f is increasing. If f prime is less than 0, f is decreasing. If the second derivative is less than 0, we know f is concave down, and if the second derivative is greater than 0, we know f is concave up. Okay, so just a few things. Let me see this part right here. This is kind of a neat little applet that shows, actually, in this case, they're global extrema. It's really local extrema. The first graph on the far left block is the graph of f. The middle block is the graph of f prime, and the third block is the graph of f double prime. And as we move the slider, you can see clearly what's happening at each point. As we draw the tangent line, the red tangent line on the parabola, as it moves, we see the derivative in the middle graph being negative, increasing. There it hits 0, and there it starts becoming positive again. So we see right at that local extrema is the key point, right? Right there where the derivative hits 0. The red line is tangent. It's a local min. We see the derivative swing from negative to 0 to positive. Derivative is negative, 0, positive. Well, that's the key idea in this first derivative test. Okay, so we'll identify a few more things and then we'll get into the test. All right. We should have an idea also between the difference of local extrema and global extrema. So we know that f of c is a local minimum for f if and only if f of c is less than or equal to f of x for all x in that interval. I'm going to go quickly through this since this should still be fresh from a couple chapters ago. We know that f of c is a local minimum, or excuse me, a local maximum if it is greater than or equal to all values. And note too, we do have the equal sign in there. You know, I mean, if you had a horizontal line, every point on that line would be a local minimum and or a local maximum if we had it like that. It's kind of a weird and broad definition, but we have that. Global extremas, on the other hand, do not have to occur over an interval. They occur over the entire domain, or from negative infinity to positive infinity if that is the domain. Okay, so f of c would be a global minimum if it were less than or equal to f of x for all the x values in the domain of the function, and likewise for maximum. By the way, keep in mind you can hit pause on this recording if you need to fill in notes or at any moment in time. A big note is to locate global extrema. We first find local extrema, and since local extrema have to occur over an interval, but globals do not, we compare them with the endpoints. The endpoint y values, right? Because extremas are function values. Okay? The extremas are function values. They are not x values. Okay. Reminder as to what a point of inflection is. A point of inflection for f is where the curve changes concavity. Okay, so it might go from concave up to concave down, or concave down to concave up. Okay, what occurs at a point of inflection? Well, if it goes from concave up to concave down, or concave down to concave up, that means f double prime must be changing sign. Okay, so it's got f double prime has to be changing sign, so it's probably going from, positive to negative or negative to positive, right? So we'll get back to looking for points of inflection in a bit, but the candidates for points of inflection then would be, if f double prime is changing sign from positive to negative or negative to positive, then f double prime of c would have to be equal to 0 or undefined. Really, the candidates are critical points, but critical points for f prime. Oops. Critical points for f prime, not for f. Okay, so you might want to pause and make sure you've got all the preliminary information because now we're going into what's called the first derivative test to determine local extrema. Okay, and it should make entire sense to you. All right. So first derivative test. This means we're using the first derivative to test for local extrema. Okay, that's what we're doing with this test. Using the first derivative to test for local extrema, henceforth abbreviated L dot E dot. Okay, so you know that candidates for local extrema are the critical points. So that's where we start. We find the critical points. We find the critical points. And again, this is where f prime of c equals 0 or f prime of c is undefined. Then what do we do with those? We test them. So what's really happening at a local extreme? Well, back to this graph, okay? What's happening in the second graph at a local extreme? We see that the second graph, there's our critical point right there. It's equal to 0. The first derivative is equal to 0, but before and after it, we see a sign change. That has to be occurring at a local extreme. A sign change in f prime has to occur because the curve, the original curve, has to go, as you can see over there, it's going from decreasing to increasing. So we look for a sign change in f prime. Okay? So that's the second step. Okay, and that's the first derivative test. Except we're going to show it, we're going to make sure that it's written really clearly. Okay, and that's the challenging part, just keeping everything straight and convincing your reader that you have in fact found a local extreme. Okay, so let's do it. Here's the first problem. 4x cubed minus 18x squared plus 24x is what f of x is. Okay, so we want to manually sketch it. We know generally that it looks kind of like this, right? Positive valued cubic. But remember in pre-calc you were told, oh, you can't find those highs and lows. You don't know where they occur. Well, now's your turn to find out where those highs and lows occur. You know, you don't need a calculator anymore. Calculus is here at the rescue. So we are going to use the first derivative test to manually sketch this thing, which means we're going to find exactly where those maxes and mins occur. So the first step is find f prime, and that will be 12x squared minus 36x plus 24. Okay. And we look for critical points because they're the candidates for local extremes. So we'll factor out 12 x squared minus 3x. Don't you love how these problems are so contrived? I wonder what percentage of the actual polynomials are factorable. Probably not many. So there we have f prime of x completely factored. We find the critical points for f to be x equals 2 and x equals 1. Those are our critical points. And so now we need to test them. Okay, we know maybe something's happening. We figure it probably is by the looks of it. We know it's a cubic, but we need to show a test, and we label Every time you use this test, you must label it. First derivative test for local extrema. Okay? First derivative test for local extrema. So remember, first derivative test, okay, in the cloud, we look for a sign change in f prime around the critical point. Okay, if you have a sign change, you've got a local extreme. If you don't have a sign change, you do not have a local extreme. Okay, so we look for a local or for a change in sign. So we say clearly to our reader, if x is less than 1. Now this in calculus, this means just a hair less than 1. It doesn't mean 0 or -1 or 10 or anything else. It means I'm just less than 1. So, you're like at 0.99 or zero point 0.9, somewhere around there. Okay? We say if x is just less than 1, then what is this stuff? Okay? So we see this, the x minus 1 will be negative, and x minus 2 will also be negative. So we can say then that product is positive. Okay? Pretty obvious to the reader. If x is greater than 1, then this product, we know what it's going to be, but we'll show it anyway. So it's like 1.1. You're putting in 1.1. That x minus 1 factor will be positive. We are not a lot bigger than 1. We are just a little bit bigger than 1. We're still less than 2, so that's going to be negative. X minus 2 will be negative. That product then is less than 0. I think that's pretty well stated, pretty obvious to the reader. You need to emulate the way that is written and be 100% clear as to what's going on. Well, we see a sign change, so we can make a conclusion right now. We see a sign change in f prime. It goes from positive to negative, which means f goes from increasing to decreasing. Notice I ordered the inequalities to start less than 1, and then I moved to greater than 1, so that I could say the curve goes now from increasing to decreasing, which means a local max at x equals 1. Okay, first derivative test on that critical point. Well, the next step, you do the same exact thing for the second critical point. You say if x is less than 2, and this means just barely less than 2, like 1.9, then 12 times x minus 2 times x minus 1, that's negative, and this one is positive. That product is less than 0. You could have used the one before if you wanted to combine them, but if you just want a simple one-sided inequality, you can just state x less than 2. And then if x is greater than 2, we have 12 times x minus 2 times x minus 1. We know if we put something like 2.1 in, the x minus 2 factor will be positive. The x minus 1 factor will be positive. We have an increasing curve again. And we can make a similar conclusion and say there is a sign change in f prime going from this time negative, or f is decreasing, to positive, f increasing. Therefore, we have a local min at x equals 2. And so right now, what's really cool is we have all of this wonderful information. We have the fact that at 1, at x equals 1, we have a local max. And at x equals 2, we have a local min. Let's see where this graph crosses the x-axis. It's 24. No, 0. There we go. Yeah, so we have roots. Yeah, we have roots at 0. So it's coming through like this. Max at 1, min at 2, and back up. And then in order to find what that actual max and min are, we just need to plug in 1 into our function and find what that is, and 2 into our function to find out what it is. At 1 it is 8, and at 2 it is 10. Excuse me, at 1 it's 10. Yeah. And at 2 it is 8. Okay, you can just take f of 1 and f of 2 and plug it in. Okay. F of 1. Just checking. Negative 14. Yep. Okay. So that's the first derivative test for local extreme. First derivative test for local extreme. Now, the second point of interest here is that point right there. Where does that occur? It looks like at 1.5, but do we know that for sure? So what we're going to do is find that point of inflection by once again using a first derivative test, even though we're going to be looking at the second derivative. So when we find the point of inflection, we find first critical points for f prime. That is where f double prime of x is equal to 0 or undefined. In this case, we won't have any undefined ones because it's a polynomial, but we will have points where f double prime is 0. So we look up here, f double prime is going to equal 24 x minus 36. 24x minus 36. So the critical point for this thing happens to be 36 over 24, or 1.5. Okay, it probably is a critical point, but we're going to show a test just to be sure. Not all the functions are this obvious. So we label first derivative test for point of inflection. First derivative test for point of inflection. We say if x is less than 1.5, then f double prime of x, which is equal to 24x minus 36. You can see that if we put in, let's see, take out a 12, it might look a little obvious, more obvious, yeah. We can say if x is less than 1.5, this factor right here will be negative, and therefore that product will be negative. And if x is greater than 1.5, then f double prime of x, which is 12, times 2x minus 3. So that's going to be positive, and therefore the product will be positive. So here we see a sign switch in F double prime. F double prime switches sign. It goes from concave down, or it goes from negative to positive, which means F goes from concave down to concave up. So that completes our first derivative test for both points of inflection and local extrema. Okay? A few little sidebar notes. Please do make sure and label your tests when you use them. Show beforehand finding the critical points very clearly. Label your tests. Show all the steps really clearly. What's going on? You can't just assume that the derivative is positive or negative. You need to show it. Okay? You must show the derivative being positive or negative clearly. Okay? And then set first derivative test for point of inflection. Find the critical points for f prime. Critical points for f prime. And then test them. Left and right. The first derivative test is really an interval test. Okay? The first derivative test is an interval test. You test left and right. Look for sign changes. Okay? If you're looking for local extrema, you look for sign changes in f prime. If you're looking for points of inflection, you look for sign changes in f double prime. Okay? That's about it. And it should make a lot of sense because you guys know what the derivatives tell you. So together with your partner, I'd like you to work this one, x to the fifth minus 5x cubed. I would like you to find first critical points, show a test for local extrema and inflection points, and graph it manually. You can then check with your TI, and if I get a chance, I'll give you a copy of the key for that problem. Okay? Your homework is this worksheet right here, first and second derivative tests homework. Okay? Just numbers 1 through 5 on that worksheet, which was found on Moodle. Or you can copy them here. Okay? There they are. Okay? You're just running the first derivative test on these 4 functions and answering 5 to graph 1 through 4 using the first derivative test to find local extrema and points of inflection. Okay? Well, I missed you, and I will see you next class period. Take care. Make sure you practice this stuff and write it up neatly. This has been a weird experience talking to an empty room. See you guys. Bye.